Hello. Hello, I'm Kushang and I'll be presenting the initial pitch for the course project of topics in applied optimization. I will begin with explaining why we need end-to-end learning in the first place and then move forward with the existing methods that are already present for end-to-end learning and then explain the method proposed in the paper and then move forward with the results and weaknesses in the paper. So, yeah. Right. So when machine learning models are used in real life, they're often used in a decision-making process. This decision-making process often uses a two-stage approach, where first an ML model predicts the key parameters of the process, which are then fed into downstream constrained optimization tasks, which gives us our final optimal decisions. This separate training usually results in suboptimal decisions because it might often happen that the suboptimal decisions happens because uh, the ML model, which is trained on predicting the key parameters, focuses on minimizing the error in the parameters, but that does not necessarily mean that uh, the decisions which are made in the downstream optimization tasks will be optimal. So there is a separate. It's a two. It's separated into two stages, because of which it is not necessary that we get the ultimate goal. Now, uh, yeah, I'll give a real life example of where this can be used. Suppose take the scenario of a robotic arm where we have a policy network which predicts specific parameters that control the robotic arm. These parameters are then used in an optimization process which calculates the exact torques needed to move the arm along a desired path. Now, this desired path is called as trajectory tracking. Right now, this current process is split into two separate parts. First part is the policy network, which predicts the control parameters, and second part is the optimization layer, which uses those parameters to solve for the arms movements, which will decide the trajectory. Now, currently, there is no uh, feedback in the sense that there is no gradients flowing from the optimization process back to the policy framework, since both the processes are separated and it's a two-stage process. So during learning, both these processes are disconnected from each other. Now, this is where end-to-end learning comes into play. It basically uh, uses a predict then optimize framework. Instead of directly minimizing the decision, instead of directly minimizing the error, instead of just minimizing the error, prediction error, it directly minimizes the decision error along with the prediction error. So as you can see, this is the loss function for end-to-end learning as given in the paper. The first term is the decision error, which is also called as regret. Here, zy star is our optimal decision, which the model will give eventually using the key parameters, which are y, and the predicted parameters y star. Now, the beta term balances the loss between both of these terms so that at the end of the training process, we have a balanced model which gives importance to both the error in regret and the error in predictions of the key parameters. It trains the ML models, predicts the parameters along with the optimization models, which gives out the decisions. Uh, Comparing this to the loss function in the two-stage process, we have only the error in the predictions. This can be seen as a lower bound on the end-to-end learning's loss function, which is again suboptimal which is suboptimal because it's a lower bound on the end-to-end learning process. How this can be used in a robotic arms example is such that making the system end to end, where gradients flow from the optimization layer back to the policy network, would allow the entire pipeline to learn together. This means that the policy network can adapt to its predictions based on how well the arm moves or the arm doesn't move, according to the output of the optimization model. It will learn to make better predictions faster, leading to more efficient and effective control over the arm. In simple terms, having an end-to-end setup allows the system to continuously adjust and improve itself as a whole, rather than having two separate steps that don't help each other improve in the learning process. Now, there are already existing works in end-to-end learning. They do this usually by two methods. One is explicit and one is implicit. Now, explicit methods are techniques where the optimization process is unrolled over several iterations to solve this problem. Now, unrolling here means that treating each step of the optimization algorithm. Let's say we have gradient descent. Now, treating each step of the optimization algorithm as a layer in a computational graph, similar to how you would do it in a neural network, similar to how you would do it in the layers of the neural network. That is essentially what unrolling means. Now, we do this unrolling for each step of the optimization algorithm. Then the output from the final iteration is used as an approximate solution to the optimization problem. By doing this, an explicit computational graph is constructed where the inputs are linked to the outputs by step through iterations. Now, this can be computationally expensive because the explicit methods are usually done for unconstrained optimization problems, but doing this for constrained optimization problems would require projecting the decision variables, which are the would require projecting the decision variables onto a feasible region. Coming to implicit methods, now implicit methods use the implicit function theorem to relate the decision variable. Decision variable is basically the variable that we're trying to optimize in this scenario to other parameters in the problem. These methods often applied to the KKT conditions, which are a set of mathematical conditions that characterize the optimal solution in a convex optimization problem. uh, Existing methods are also problem specific, which basically reduce the efficiency and generalize would not be able to generalize to any use case. So examples include opnet. So opnet is a differential QP solver, quadratic programming solver, that runs on GPU operations. It uses implicit differentiation on QP problems, making it suitable for optimization. There is another example called diffCP. It computes the derivative of a convex cone program by differentiating the residual map of its embeddings. This approach is often used to handle problem, uh, problems involving complex constraints in the optimization problem. Coming to the approach that BPQP uses. Now, BPQP is also based on the implicit methods which are previously used, but it basically builds on the previous implicit methods and introduces a more efficient approach. Now, in the backward pass of the BPQP, it simplifies the gradient computation by reformulating the original problem into a simpler QP problem. It solves the KKT matrix using a matrix inversion method without relying on the forward pass. So basically, what happens is there is a dependency of the forward, there is a dependency of the backward pass on the forward pass. So BPQP separates the computations for both the forward and backward passes, which makes each step easier to solve and more efficient. It does not rely on information sharing between the both passes, uh, which makes it efficient. Yeah, which eventually reduces computational cost, which would also improve scalability a lot. Yes. Moving on. So the methodology behind BPQP is that once we differentiate the loss function, so we had the end-to-end loss function. So once we differentiate the loss function through the KKT conditions, we would end up with a matrix of linear equations to solve, which look like this in the slide, as you can see. Now, directly solving this linear system of equations is very computationally expensive. What BPQP does, BPQP's full form is backward pass as quadratic programming, right? So what it does is it just reformulates this linear system of equations into a QP problem. Now, how it does this is, since the backward pass eventually is being solved after the forward pass, we change the inequality constraints into an active set of equality constraints, and all the inactive set is discarded, which basically boils down to the resulting QP problem, which is the second matrix as shown, matrix equation as shown. Now, solving this reformulated QP problem efficiently, what BPQP does is it sticks to first order optimization algorithms like ADMM instead of second order optimization algorithms, because using first order optimization algorithms allows for scalability when we are working with larger data sets. Uh, yeah, this is made possible because the backward and forward passes are now decoupled and they're separate, and there's no dependency of each other on one of them. The weaknesses in the paper are more towards the experimental sides of the paper. So, in the experimental conditions and in the results that the paper proposes, there is one experiment that the paper does is on real world portfolio optimization, which is an interesting problem to work on. But the task in the modern portfolio that they're trying to solve is very simplistic, which is basically just learning the correlation between different strategies of the real world portfolios. We will try to apply this problem on a harder prediction task, which would help us see how BPQP is efficiently solving the real world portfolio optimization problems in a difficult setup. The second weakness in the paper comes with the experimental conditions that the paper employs. Initially, we can see that in the introduction section, they propose major claims in proving the LP results. It says that it's 21.17 times faster but this is very misleading because since one version uses a quadratic term and one version uses a linear term. So our goal would be to verify the claims that the paper holds in terms of the result section and rerun the experiments and make sure that the environment in which the experiments are being conducted is fair, and yeah, basically rerun the experiments and figure out like in a fair setup and verify the results which are claimed in the paper. There is also a key theorem in the paper, which is so as we saw previously in the methodology, they solve this backward pass by removing inequality constraints and to an active set of equality constraints. So this gives rise to a theorem in the paper. This theorem they've mentioned in the paper, but they've not given a proof for it. We'll try to demonstrate a rigorous proof for this and show why this holds true. Yeah, thank you.